Welcome to the Deep Dive. Today we are looking at a machine that is, well, it's more than a machine, it's a masterpiece of modern engineering.
Absolutely.
We're going to try and unlock the secrets of the world's most advanced fighter jet, the F-35. Our mission is to take you inside using our source material to really uncover the incredible engineering, the manufacturing, and the tech that makes this thing fly.
And not just the jet itself, but the insane physical demands it places on the people who fly it.
Exactly.
This is a complete look behind some very, very secure doors. And the story, it really begins with scale. We start this deep dive at U.S. Air Force Plant 4 in Fort Worth, which is run by Lockheed Martin.
And when you say scale, you're not kidding. The facility isn't just big, it's immense.
It really is.
The footprint is about 3 square kilometers. To give you a visual, that's roughly the size of Central Park in New York.
Right. And it has this incredible history. This isn't some new factory they just built.
No, production here started way, way back in 1942. They were building the B-24 Liberator.
A hugely important bomber in World War II. And that lineage is key. You can trace the evolution of American air power right there.
Yep.
From the B-24, they went to the B-36, then the classic F-16.
Everybody knows the F-16.
And the F-22 Raptor. And now, since 2004, it's been all F-35. It's just decades of engineering evolution all under one very, very big roof.
And what a roof. I mean, the assembly line itself, it's a mile long.
A mile.
Just think about that. That's about the length of the Brooklyn Bridge. Or, if you prefer, 17 soccer fields laid end to end.
And on that line, at any given moment, there are over 100 of these jets in different stages of being built.
Wow.
All supported by a workforce of more than 18,000 people. It gives you a sense of the constant global demand for this aircraft.
So what are they building? The F-35, it's famous for its stats, right? The speed is just, it's crazy. Up to 2,000 kilometers per hour, Mach 1.6.
But the real defining feature, the reason it exists, is stealth.
Right. It shows up on military radar as something the size of a golf ball.
A metal golf ball? Yeah. We'll definitely get into how they do that, the geometry, the paint. But the tech inside is just as wild. We're talking about a helmet that costs $250,000.
$250,000.
And it projects all the data navigation, targets, everything right onto the pilot's visor. That's the kind of precision we're dealing with.
Okay, so let's unpack that. If the jet needs that kind of performance, the construction has to be, well, perfect. You can't be off by a millimeter. So where does that obsession start?
It starts in a place called the metrology lab.
Which is the science of measuring things, right? Not meteorology, not the weather.
Exactly, metrology. And if you want a quick idea of the complexity, just think about the fasteners.
The screws and bolts.
A single F-35 has 40,000 of them.
40,000, and every single one has to fit perfectly. So why? I mean, what's the reason for that obsession?
It's really twofold. First is just pure structural integrity. But second, and this is the big one, stealth depends entirely on perfect geometry. If even one panel is misaligned by a tiny fraction, you create a little corner that reflects radar waves. Your stealth is gone. The measurement is the defense.
So they use all this cutting-edge spanning tech. They basically digitize the space where a panel goes to make sure it fits in a virtual model before they even try to bolt it on for real.
That's the idea. They're guaranteeing the fit before it's assembled. And quality control gets even more extreme. They have this technique where they put a special clear gel on the panels.
A gel?
Yeah, and by looking at the shadow it casts, they can see microscopic specks of dust or tiny scratches that are invisible to your eye.
Because even that could mess with the radar-absorbing paint later on.
Precisely. And it's not just the surface. Since so much of the F-35 is carbon fiber, they use these handheld scanners to find imperfections inside the material itself.
So like a tiny crack that you'd never see.
Exactly. Damage that's invisible, but could be a huge problem in the air. It's all about structural insurance.
And that structure has to hold up in wildly different environments, which brings us to the 3 main versions of the jet.
Right. You have the F-35A, which is the most common one. It's built for traditional runways.
Then there's the F-35B, which I find fascinating. The Stovey L model, short takeoff and vertical landing.
That's the one with the huge lift fan right behind the cockpit. It lets it take off from, very short runways or even small ships, and then it can land vertically, just like a helicopter or a drone.
And the third one?
That's the F-35C. That one is built for the absolute punishment of landing on an aircraft carrier.
Which is basically a controlled crash.
It really is. So the C model has much larger wings for better control at low speeds, and the landing gear is just massively reinforced to absorb those huge impacts.
So you go from this world of engineering precision to these extreme operational demands, and that's the perfect transition to the human inside the machine.
Yes.
We got a chance to see the backstage area, the pilot equipment room.
And we met Siren. She's the only female fighter jet test pilot at Lockheed Martin.
One of only 14 test pilots in the world working on the F-35 there.
Her story is incredible. Her call sign, Siren, apparently comes from a habit of setting off alarms.
Ah, that's perfect.
But her path there was just grueling. U.S. Air Force Academy, a degree in astronomical engineering, and then a year-long pilot training program where the competition for a fighter slot is just brutal.
It's a world where experience is everything. We also heard from another pilot, Seeker, an F-16 guy with 6,000 flight hours.
6,000 hours.
And his scariest moment wasn't combat. It was being in the Middle East and getting caught low in a sudden sandstorm.
Mother Nature.
Yeah.
Just shows you the risks they're always navigating.
And before they ever face a sandstorm, they train for endless hours in the simulator. The controls look simple, just a stick and throttle, but they manage almost everything.
And that throttle is the key to just unbelievable power. You push it all the way forward, the afterburner kicks in, and you get 43,000 pounds of immediate thrust.
It's not like accelerating in a car. It's an instant, violent shove.
The pilots describe it as strapping yourself into a controllable rocket.
And the weapons are simple. Red button for a missile or bomb, trigger for the gun. But the real challenge isn't the weapons, it's the G-force.
Right. Normal life is 1G. The F-35 can pull up to 9Gs.
So that's 9 times your body weight pressing down on you. It's like having a bear or 9 people sitting on your chest.
And what that does, physiologically, is it forces all the blood from your head down into your legs.
Which leads to tunnel vision, right? Like you're looking through a straw.
And then G-lock, which is passing out. And in a fighter jet, that is catastrophic.
So how do they fight that?
The solution is the G-suit. Or G-pants, really. It provides about 1 to 1.5 Gs of extra protection on its own.
But the suit doesn't do all the work, does it?
Not at all. The suit has these air bladders inside that inflate automatically as the jet pulls Gs. They squeeze your legs and abdomen to physically push the blood back up to your brain.
Okay, that makes sense.
But for those really high G maneuvers, like 8 or 9 Gs, the pilot also has to perform this special breathing and muscle tensing technique.
The anti-G straining maneuver.
Exactly. You're forcefully contracting all your muscles in your core and legs while doing this very specific controlled breathing. If you don't do it perfectly, while the suit is inflating, you pass out.
The machine literally requires you to be at peak physical performance just to stay conscious.
And the mental strain is just as exhausting. Siren said her longest mission was almost 12 hours.
12 hours of 100% concentration.
While your body's fighting physics.
Let's shift from that internal battle to the machine's external battle. I mean, the whole reason for this demanding performance is so the F-35 can dominate, and that comes from stealth and sensor fusion.
Right, let's dive into the stealth. It really defines the entire aircraft. Every edge, every corner, even the paint is designed for it.
We know the shape deflects radar waves, but what about the materials?
It's all about the radar cross-section, or RCS. And the F-35's is just, it's shockingly small, 0.0005 square meters.
Okay, put that in context for us.
Well, a bird is about 0.01 square meters. A human is about 1 square meter.
So it literally looks smaller than a bird on radar. The golf ball analogy is real.
It is. And then you have the classified radar-absorbing paint, which soaks up radar waves instead of reflecting them. It's that combination of geometry and material science.
But that creates a huge problem for weapons, doesn't it? The jet can carry 18,000 pounds of bombs and missiles.
The weight of more than 4 Cybertrucks, yeah.
If you hang all that stuff on the wings, your stealth is gone. Your golf ball just became a school bus on radar.
And that's the critical design choice. To stay stealthy, all the weapons have to be carried inside internal bays. There are these 2 big sets of doors on the belly of the plane.
So to fire, you have to open the doors. Doesn't that flash your position to the enemy?
It's a calculated risk. The doors are engineered to snap open and shut in milliseconds. It's a very, very brief window of increased visibility. The pilot has to pick their moment perfectly.
And picking that moment is where the jet's brain comes in. Sensor fusion.
This is the real magic. This is what separates it from older jets like the F-16, where the pilot had to do all the work.
What do you mean?
Well, in an F-16, the pilot is looking at different screens, radar, sensors, maps, and they have to mentally build a picture of what's happening. They're an information processor.
Okay.
Sensor fusion does that automatically. It takes data from every sensor on the jet, fuses it all together, and gives the pilot one single, simple picture of the battlefield.
So the F-35 pilot isn't processing information. They're
making tactical decisions. The jet tells them what's a threat and where it is.
Yeah.
It's a massive leap in situational awareness.
And the place they see all this is the helmet. The Gen 3 helmet-mounted display.
It's a $250,000 helmet.
Which is basically a Lamborghini for your head.
And it has to be, because it's not just a screen. It's an actual sensor used for targeting. That's why every pilot's head is 3D scanned so the helmet fixes them, and only them, with absolute precision.
And then there's a see-through feature.
It's incredible. It pipes feeds from cameras all over the outside of the jet directly to the visor.
So the pilot can look down and see the ground right through the floor of the cockpit.
Exactly. It uses a system of infrared cameras to create a seamless 360-degree bubble of vision around the plane. You can look through the jet's own body to track a target below you.
As Siren said, it's like being Wonder Woman for a little while.
But with a top speed of Mach 1.6. It's a true marriage of human and machine.
So as we wrap this up, I keep coming back to Siren's perspective. She said she thinks of herself as a fighter pilot, not a female fighter pilot.
Right.
But she also knows that being that representation is important. It's proof that this level of performance is possible for anyone.
And what we hope you've taken away from this deep dive is that sense of unparalleled precision, from the metrology lab to the sensor fusion software.
We've talked about the $250,000 helmet, the G-suit you need to survive 9 Gs, and the mental challenge of staying focused for 12 hours straight.
And that brings us to the final thought. There's a real tension here between the human and the technology.
You have a machine that can fly at Mach 1.6 and pull maneuvers that are designed to make a human being pass out. A biological failure that requires a special suit and intense physical training just to counteract the laws of physics.
So the question for you to think about is this. What does it mean for our own limits when we build technology that is designed, literally, to push our bodies and our minds to the absolute breaking point? This jet isn't just an engineering triumph, it's a constant high-stakes experiment in the boundaries of human endurance.
Thank you for joining us on this deep dive. We'll see you next time.